Yep. We are going today to learn the fundamental theorem of calculus, and this is a huge, huge deal. Now, the fundamental theorem of calculus has two parts, and we're going to talk about part one today. Before we do the definition, though, we're going to go down here, and you'll notice I've already started, and that's because I forgot to start the recording. So, we're looking at the line y equals negative 2x plus 3. Now, it says to calculate the definite integrals, but we're not going to calculate the definite integral first. What we're going to do is we're going to go from x equal negative 2 to x equal 1. We're going to stay above the x-axis, and that's the area I shaded in. And what the students are doing right now is finding the area of that shape. Now, that shape is a trapezoid. Do you have to do this as a trapezoid? No. How could you break that up? You can do a rectangle and a triangle if you want. Fine. What are you getting for area then?
12. Yeah.
12? Okay, I'm hearing 12. Your square units, don't worry about that. Since they're not given, we don't worry about them. Once you get that one done, I want you to go down and do the same thing to this one, but we're going from 2 to 5. That's right. Now, this is below the x-axis, so your answer is going to be negative because the heights of all of your pieces, if you were doing rectangles like Riemann sums, the y values would all be negative. So all I want you to think is this region is below the x-axis completely, so I know that area will be considered negative. Oops, come on, Stina, get a grip.
It can be under or below the line, but it's always above the x-axis.
Oh, I can have a shape that's partly above and partly below. And I'll teach you how to do those. This one equals 12 as well? Well, okay, so Wendy says that area is 12 as well, but it would have to be negative because the whole thing's under the x-axis. I'll give you a minute to kind of finish that up. So, now, I'm going to show you something. Watch and be amazed. I'm going to show you the fundamental theorem of calculus, and then we'll write it up. The fundamental theorem of calculus says that this is equal to negative x squared plus 3x, evaluated from negative 1 to 2. 1 squared is 1, opposite of that is negative 1, plus 3, minus negative 2 squared is 4, opposite of 4 is negative 4, minus 6, that's 2 minus negative 10.
Whoa. Okay, now.
And that is 12. And that is 12. Let me do the other one. What's the first thing you saw me do? The integral or the antiderivative. That's right. So what did I do? I took the antiderivative. Now notice I didn't put the plus c on it. I'll explain that to you in a minute. I evaluated that antiderivative at x equal 1, the upper limit of integration. I evaluated that antiderivative at x equal negative 2, the lower limit of integration, and I subtracted. That, ladies and gentlemen, is the fundamental theorem of calculus. Okay, let's walk through this one. I'll give you time to write this down. So, all right. The integral of from 2 to 5 of negative 2x plus 3 dx is antiderivatives negative x squared plus 3x. I'm evaluating that from 2 to 5. So I'm going to evaluate that antiderivative at 5. 5 squared is 25, opposite of that's negative 25, plus 5 times 3 is 15, minus I'm going to evaluate that antiderivative at 2. 2 squared is 4. Opposite of 4 is negative 4. Plus 3 times 2 is 6. So that gives us negative 10 minus 2 is negative 12. Thank you very much. Thank you very much. Isn't that awesome? I loved it. I loved teaching this the first time. All right. So I'm going to make sure that I do all this right. The fundamental theorem of calculus, one part of it, says if f of x is continuous on the closed interval from a to b, no comma, and big F of x is the antiderivative. Did you write big, B-I-G? Okay. Derivative of little f of x, then the integral from a to b of little f of x dx. Remember, I take the antiderivative. The antiderivative of little f of x is this big F of x, right? It's the antiderivative evaluated at the upper limit of integration minus the antiderivative evaluated at the lower limit of integration. I don't know why, because I thought, why don't we just make that f prime? I don't know. I decided to do it this way just to stay consistent with his notes. Now, I want to show you where the plus c went, because students usually ask about that. You don't write anything down, just let me show you how this works. If I took the antiderivative of this thing, and I negative x squared plus 3x plus c, evaluated from negative 2 to 1. Now remember, these are x values, negative 2 and 1. So that would be negative, what, 1 plus 3 plus c minus negative 4 minus 6 plus c. Do you see that those c's would just subtract out because they're the same constant? So there's no point in writing it down every time because they're just going to subtract out anyway. All right, next page. Now what I want you to do, we're not going to actually calculate the area, you know, using rectangles and trapezoids, but I want us to draw the area so you can be aware of what you are finding the area of. Same function, but we're going from negative 1 to 4. So this one looks like this. Now, I want you to think before we start doing, although it looks like some of you have started, that's okay. I want you to try to just approximate what you think the area might be when we get finished doing the fundamental theorem of calculus. Keep in mind you've got area above the x-axis and you've got area below the x-axis. It's going to be pretty close to 0 if it's not exactly 0. All right, so this integral, well, we've done the integral several times. I mean, excuse me, the antiderivative, same thing, I guess. We're going to evaluate this from negative 1 to 4. Now remember, you always evaluate at the upper limit first, minus evaluating at the lower limit. So upper limit what's that, negative 16 plus 12, minus the lower limit, negative 1 minus 3. So what's that, negative 4 minus negative 4? Dun, da, da, da. 0. Questions? Okay. Go to the next one. Yeah, if you, yeah, Miss Lashley would be proud if you thought about a little geometry and thought about a rotation right there, right? Negative 1 to 3. Negative 1 to 3. I don't want to protect snap. That's not what I want. I want a crayon. Can you come up with something that you think is true about the answer that you should get? Positive, I agree. All right, so we've got negative x squared plus 3x evaluated from negative 1 to 3. What's that, negative 9 plus 9? Is that right? Minus negative 1 minus 3. Is that right? Negative 9 plus 9 minus negative 1 minus 3. Yep. 4. Yes? No? Yep. Okay. Next one. From 0 to 5. You get negative 10. Okay, let's go to the next page. Based on the results of the 5 previous examples, what inferences can you make about the value of definite integral and the amount of area bounded by the graph of the integrand and the x-axis? I'm just going to show you what he's talking about. Okay, so he says we can make 4 inferences. So 4 inferences. I will be able to do one at a time, and then I'm going to have to erase. The integral from a to b. Yeah, you're going to, well, here. The integral from a to b of f of x dx is the area. This is just the definition, okay? The area of the region bound by the x-axis, f of x, x equal a, and x equal b. That's what we're finding when we actually do an integral. Now, every one of these is going to have that part at the beginning. That integral equals 0 on a to b if what?
It's the area above or below the x-axis.
That's right. If the area above the x-axis equals the area below the x-axis. Bless you. Next. That integral is positive on the closed interval a to b if
The area below, I mean above the x-axis is more than the
that's right. If there is more area above the x-axis than below. I think you can probably figure out what the next one's going to say. That's all right. That's cool. All right. Is less than 0 on that closed interval if there is more area below the x-axis than above. Correct. All we're going to do is practice. Now, I mean, if our shapes that we're finding the area of have straight sides, we could just use geometry. We'd never have to worry about calculus. But I guarantee you there are a whole lot more shapes out there that are don't have lines as their sides. This one obviously has curves because it's got x squared in it. But we can still calculate the area under the curve. And we do it with the fundamental theorem of calculus. So let's do it. What's the antiderivative of that function? X squared minus 1/3 x cubed. Good. And we're going to evaluate that from -1 to 2. That is all the calculus you have to do. The rest of it's arithmetic. Yeah, crap. 2 squared is 4, minus 2 cubed is 8, 8 over 3, minus 1 plus 1/3, is that right? What's that give me? 4 minus 8, 4 minus 8/3 minus 1 minus 1/3. What's that? 3 minus 9/3? Isn't that 9/3? Because aren't they both negative? What did I do? What did I do? Did I do something wrong? Didn't I? I'm right, aren't I? Okay, I'm just checking. Okay. 4 minus 3, or 4 minus 1 is 3. Negative 8/3 minus 1/3 is negative 9/3, which is 3, right? Same thing. No problem. No problem. Okay, next one. On a problem like this, I'm going to do a rewrite first, and I'm going to rewrite it like this. It's much easier for me to take an antiderivative with a negative exponent than with a fraction. What's that going to be? X to the -1 over -1. I'm going to leave you to evaluate that because I want to pull up my calculator for a minute. So -1/3 plus 9/2, is that right? Minus 2, is that 2 plus 2? Is that right? Wait, what? Wait, 3, that's -1/3. 3 squared is 9, 9/2. All right. 2. So that's 1/2, right. Negative 2 squared is 4. 4 times a half is 2. Is that right? Is that right now? Listen, I'm going to do it like this. I'm going to do negative 1/3 plus 9/2 minus 1/2 minus 2. What's that give me? This is what? 4. 4 minus 2 is 2. And 2 minus 1/3 is 5/3.
That's how I thought about it.
Excellent. Excellent. Yeah, for real. Okay. 2 o'clock. 2 o'clock. Okay. Is that all that's on that page? Yeah, but that's the one I was looking for. Okay. All right. You know how to take an antiderivative like that. What do you have to do to do a rewrite? Separate first. So this is going to be the integral of 1 to 4. That's 2x over x squared plus 3 over x squared. Yes? So that's the integral from 1 to 4 of what? 2 over x, which we're going to write as 2x to the negative 1 plus 3x to the negative 2. Now I'm going to back up and I'm going to change my mind and I'm going to write that back as this. Why? Because if I write it like this, do the antiderivative. That's going to be x to the 0 over 0. Remember? When you have that, look, what is the integral of 1 over x dx? Natural log. That's the natural log of x. So that's 2 natural log x. Does he, I want to see if he does, yeah, okay. So this antiderivative is 2 natural log x. Now, what's the antiderivative of this next piece? It's going to be x to the negative 1.
So negative 3 over x to the x. Yeah.
Negative 3x to the negative 1. Or negative 3 over x. And that's how I'm going to do it in order to evaluate. Do you have any questions? It does, yeah, for sure. You got to think about it. Okay. So I've got 2 natural log 4 minus what? Minus 3/4, and I don't have enough room here, minus 2 natural log 1 minus 3. What's that? What's the natural log of 1?
Oh, wait.
E to what power is 1? 0. That's 0. Bye-bye. So this is going to give me 2 natural log 4 minus 3/4 plus 3. What's 3 minus 3/4? 2 1/4. So 9/4. So this is 2 natural log 4 plus 9/4. Leave it. Leave it. Do you have questions? Uh-huh. Some of you will. You're going to forget it, but as soon as you get it wrong on your first quiz, you won't forget it again. Now we're going to go at this from a table. Pictured below is a table of values that shows the values of f, f prime, and f double prime for selected values of x. Use the information in the table to answer the questions. Did I skip one? Well, snap. Yeah, I guess we better. I forgot one. Yeah, we can't leave out the trig one, can we? You know something we should have paid attention to on that last one? The fundamental theorem of calculus had something important in it. It's not on that page. Don't forget that piece. Now, here's the deal. None of the ones we have done so far have had an issue. That's discontinuous at 0, but 0 is not on the interval. So that's something just be mindful of. This one's never discontinuous because it's a polynomial and a trig function cosine. All right, what's the antiderivative? Good. X squared plus sine x, evaluated from 0 to pi. So that's pi squared plus sine pi minus 0 squared plus sine 0. Yep. What's the sine of pi? Ah, the sine of pi is 0. So this is pi squared. That's 0. That's 0. What's the sine of 0? Pi squared. That's not bad. That's not bad. Oh. What? I'm going to turn this off for. Let me show you real quick why I pulled the calculator up. You can use this at this point to check only, but I am not going to allow you to use your calculator for anything else at this point. Do you hear me? Do you have your calculator handy? And if you don't, oh well. Oh well. Yeah, you can just watch. You can just watch. Math, option 9. So if we do the integral from -1 to 2 of 2x minus x squared and evaluate that with respect to x, that's 0. If you, now listen, most of the time it's going to give you 0. If you see this capital E, it means times 10 to a power of, scientific notation. That means you got to move the decimal point 14 places to the left. There's a glitch in these calculators somehow. That's 0. You see e to any big negative number, that's 0. That's all you got to do. It's math option 9. No, it truly is 0. Truly is 0. Don't know what the calculator's doing, but that truly is 0. But that's math option 9 on your calculator.